noonday sun or the stars at dawn or dusk, these celestial bodies have guided man since he first sailed the seas. Modern-day electronic systems bring continuous position references to the fleet. Systems like LORAN and inertial navigation. Accuracy? Excellent, under the right conditions. Time and weather, for example, complicate visual celestial observations. So do environmental problems inherent in the deployment of our missile-carrying underseas fleet. Navigation by satellites launched into space breaks through these restrictions.
8, 7, 6, 5, 4, 3, 2, 1.
Today, orbiting satellites of the Navy Navigation Satellite System provide round-the-clock, ultra-precise position fixes from space to units of the fleet everywhere in any kind of weather. Navigation by satellite. How and why does it work? First, a little astrophysics to answer why. Any satellite, man-made or not, remains in orbit because the force with which it is trying to fly away from Earth is matched by the gravitational pull of Earth. So it continues moving around Earth in an orbit whose path conforms very nearly to the classic laws of Sir Isaac Newton and Johann Kepler. Suppose we put a radio transmitter in the satellite. You'll detect that the radio frequency is Doppler shifted while the satellite passes by. The Doppler effect shows up as an apparent change in frequency and is caused by relative motion between the satellite transmitter and the receiving antenna on Earth. While the satellite is approaching, the received frequency is higher than the one actually transmitted. The wavelengths are compressed by the velocity of the approaching satellite as the intervening distance narrows. As the satellite nears the point of closest approach, the received frequency descends rapidly to match the one we know is being transmitted. As the satellite goes away, the received frequency continues to drop. Doppler shift can be plotted, frequency versus time, to produce a unique curve, which can be received at only one point on Earth at a given instant. Knowing your position on Earth, you can use the Doppler curve to calculate the exact orbit of the satellite. And the reverse is true. If you start with a satellite of known orbit, analysis of the Doppler shift as the satellite passes will tell you exactly where you are anywhere on Earth. This fact forms the basis of the Navy Navigation Satellite System. The system is more accurate than any other navigation system known today. Accuracy that can establish a pinpoint of latitude and longitude. This precision is the result of new techniques for fine control and measurement of time in terms of frequencies generated by ultra-stable oscillators. Of course, there are many astronautical problems that confront this new system. Most of these are the result of the near-Earth orbits used to produce the measurable Doppler effects on which the system depends. For one thing, the satellite does not revolve in a smooth ellipse around Earth. It would if Earth were a perfect sphere with uniform mass distribution. But instead, Earth has various bulges and unequal concentrations of mass whose attraction pulls the satellite this way and that as it orbits. For graphic purposes, we have exaggerated these irregularities. Then, too, the satellite doesn't travel in a perfect vacuum. Another problem is that the satellite radio signals do not travel in a straight line to Earth. They are bent as they pass through the ionosphere, a layer of electrically charged particles that surrounds Earth. But these problems have been solved in the Navy navigation satellite system through observation of a series of experimental satellites, beginning with the launch of the NAV-1B satellite in April 1960. The effects of ionospheric refraction have been corrected by placing two radio transmitters in the satellite in order to generate two distinct frequencies. Each frequency is bent a different amount by the ionosphere. The difference between the amounts these two frequencies are bent is the factor that the receiver uses to solve for and correct refraction error. As for orbital irregularities caused by Earth's uneven shape and off-center distribution of mass, precise tracking of thousands of orbits of system satellites over the past years and analyses of the accumulated data have enabled physicists to compute these irregularities and predict satellite orbits with pinpoint accuracy. Now let's talk about how the Navy navigation satellite system works. To cover the whole Earth, a satellite must be in near polar orbit, that is, an orbit passing near the north and south poles. As the Earth rotates beneath the fixed plane of the orbit, which passes completely around Earth, sooner or later, the satellite will pass within range of any part of the globe. With one satellite in orbit, a particular point on Earth is within range at least once each 12 hours. Ships and submarines need to know their position more frequently than this, and therefore the Navy navigation satellite system employs a constellation of satellites, each in a polar orbit. Thus, ships at sea can get a fix almost hourly, depending on their latitudes. Satellites in orbit, a ground network consisting of 4 tracking stations, 2 injection stations, and communications, operations, and computer centers, and navigation sets aboard units of the fleet. These are the elements of the Navy navigation satellite system. Let's see how they all work together. As a satellite comes within radio range, the tracking station records the Doppler shift of its signals. The tracking station sends the fresh data via the communication center and the operations center to the computer center. The computer center predicts the orbital coordinates which define where the satellite will be each 2 minutes for the next 16 hours. The computer center prepares a message containing these orbital coordinates and sends it to the injection station. From here, the message is injected into the satellite by high-power radio transmission. This updates old information stored in satellite memory and extends the navigational utility of that satellite for another 16 hours. Each satellite continuously transmits 2 carrier frequencies modulated with a description of the satellite current orbital position. The navigation set aboard ship receives the satellite data, telling where the orbiting satellite is located right now. At the same time, the navigation set measures the Doppler shift of the incoming signals to determine the position of the ship relative to the satellite and instantly prints out the precise latitude, longitude, and satellite time. The system works anywhere in the world, night or day, in any kind of weather. For every pound of satellite in orbit, there are tons of equipment on Earth that make navigation by satellite possible. Let's look at the ground system. Satellite tracking stations are located in Maine, Minnesota, Hawaii, and California. Located here at Point Mugu, California, the Navy Astronautics Group operates the navigation satellite system. The headquarters building contains the operations, communications, and computer centers. Overlooking Point Mugu is one of the system's 2 injection stations. The other one is in Minnesota. We're inside the Operations Center, command post for the Operations Duty Officer. The mission of the group, round the clock, 7 days a week, is to make sure that each navigation satellite always has correct, up-to-date information stored in its memory unit. An informative array of actuated displays shows the performance, memory, and injection status, and operating mode of each satellite, and helps the duty officer coordinate all network operations that keep the satellites broadcasting navigation data. A tracking station like this one at Prospect Harbor, Maine, is where the system cycle starts. Here, operators track each satellite pass to report Doppler observations of the orbit that will be used to improve future orbital predictions by the computer at headquarters. Tracking data is recorded on tape for transmission by TRADAT, a rapid self-checking data link 5 times faster than teletype. The operator calls headquarters at Point Mugu to alert them that a tracking message is coming. After he presses the start button, the rest is automatic. Here at Headquarters Communication Center, tracking data is received from Prospect Harbor and the 3 other tracking stations. More than 80 messages every day. A day's tracking data is turned over to the computer center, where it is logged in for processing as called for according to computer time schedules for preparing injection data for each satellite. The job of the computer center is to update satellite orbits to improve future position predictions and to prepare new messages for injection into satellite memories. Because of inaccuracies in the computed Earth model, predicted positions contain errors that increase with time. Therefore, satellite orbit data must be updated daily. Although the center's IBM 7094 Model 2 computer performs more than 500,000 computations each second, it takes about 2 hours to update the orbital predictions for a single injection message. While each satellite memory contains about 25,000 data bits, the message for several injections prepared by the computer center, which includes operating instructions for the injection station's digital equipment, contains more than 250,000 bits. Injection data must be prepared to arrive at the injection station 100% error-free and be there well before a satellite is scheduled to make its pass. From the communication center, injection messages are sent to injection facilities by IBM 7702 ultra-high-speed data link at 2,000 words per minute. At the injection facility, an identical 7702 receives the message exactly the way it was produced by the computer at headquarters. To protect the original tape, a work copy is immediately made on the data processing equipment associated with the ANUYK1 computer. This computer, familiarly called the YUK, is the heart of the injection station, controlling the digital equipment during injection. The operator and the computer use an input-output typewriter to talk back and forth. The injection station's 60-foot diameter directional antenna is pointed at the predicted rise point in accordance with commands prepared in advance by the computer center. As the satellite comes within radio line of sight, the receiving equipment locks on both radio signals. Computer recognition of special identifying words, called barker words, at the beginning of the incoming satellite broadcast establishes the start time for the injection that follows. It takes a little more than a quarter of a minute to inject enough data to last for 16 hours of successive 2-minute broadcasts by the satellite. As soon as the injection attempt is completed, the YUK will make an immediate comparison between the first 2-minute readout received from the message just injected and the same message interval retained in its memory. If they don't match, another injection is automatically attempted during the next 2-minute time cycle. The process is repeated until the computer verifies that the satellite is broadcasting the correct message. Data is transmitted and received by the injection station antenna. It is programmed to track the satellite throughout the pass. The message being injected into the satellite enables it to broadcast its position continuously each 2 minutes for the next 16 hours. But before then, about 12 hours from now, one of the 2 injection facilities will inject a new message, updating orbital data to make it good for another 16 hours. The Applied Physics Laboratory of Johns Hopkins University, Baltimore, is responsible for the design and assembly of navigation satellites. The Naval Avionics Facility, Indianapolis, accomplishes much of the engineering and fabrication of satellite components. The satellite is currently a compact octagonal spacecraft weighing about 130 pounds. It is loaded with miniaturized electronic components of receiving, transmitting, telemetry, power and memory systems. The satellite clock is in actuality an ultra-stable 5-megacycle oscillator like this one. Solid-state electronic components used in the satellite are so minute that a binocular microscope is used during assembly for the precision welding required to ensure absolute reliability under vibration and temperature stresses encountered during launch and orbit. Satellite memory units and control circuitry can handle nearly 25,000 separate bits of modulated information. The satellite gets its power from the sun. 16,000 individual solar cells convert sunlight into electrical energy that is stored in nickel-cadmium batteries inside the satellite. Before launch, these blades are installed on the satellite, folded down on spring-loaded hinges, and held in place by D-spin cables so that the whole package fits inside the rocket's nose cone. A 4-stage solid-fuel Standard Scout booster is currently used to lift the satellite into orbit. "22 minutes after liftoff, the satellite is in orbit, spinning, still connected to the last booster stage. When the D-spin cables unwrap, they release the solar blades and also slow the spinning of the satellite. The solar blades snap into place to form an X with the satellite body in the center. 5 minutes later, spin is negligible when the payload separates from the 4th stage. The small amount of spin remaining is dissipated by D-spin rods. Tumbling is reduced to 2 revolutions per orbit by ground-commanded electromagnets within the satellite that align the satellite with Earth's magnetic field. To eliminate tumbling action altogether, a 100-foot boom is extended upward from the top of the satellite, away from Earth, providing gravity gradient stabilization. This orients the satellite to keep the antenna mounted on its base, always pointing toward Earth. The Navy navigation satellite system pays off in a precise navigation fix anytime, anywhere, in any weather. On Polaris submarines, the satellite navigation equipment is designated AN/BRN-3. Its operation is virtually automatic. From the alert computations, the BRN-3 knows when the next pass will occur and pre-computes an estimated Doppler curve such as would be received at the assumed position. When the pass occurs, the navigation set receives the true satellite position and the actual Doppler curve. After filling these known factors into the navigation equation, it computes and prints out the correct latitude and longitude and the satellite time at which the fix was obtained. The BRN-3 solves for true position by adjusting and readjusting the assumed position until its pre-computed Doppler curve matches the actual curve received. Surface ships navigate by satellite too. Here, the equipment is designated AN/SRN-9, and it computes the fix in a different way. After the operator has tuned to the satellite frequency, SRN-9 automatically tracks the satellite, taking Doppler counts for at least 3 two-minute intervals. These counts and the corresponding satellite data received are used to compute hyperboloids that intersect on Earth's surface to fix the ship's position. The fix, in terms of latitude, longitude, and time of fix, is computed and printed out shortly after the satellite has made its pass. The Navy navigation satellite system is also used for scientific purposes. For example, the ship surveyor of the Coast and Geodetic Survey used satellite signals for precise navigation in the remote reaches of the Pacific Ocean. The global accuracy of satellite fixes and the ease with which they can be obtained mark a new era in the fields of oceanography and coastal charting. In Washington, D.C., the Naval Observatory also monitors system satellites to verify the accuracy of satellite time signals. These observations help maintain the strict time standards necessary for the accuracy of navigation information relayed to users of the system. The system brings other benefits too. Tracking data systematically recorded for years yields valuable information for geodesists. And as our concept of Earth's mass and physical makeup becomes more clearly defined, the computing routines that predict satellite orbits will become correspondingly more exact. The Navy Navigation Satellite System is the most precise aid to navigation known today. For the navigator, it represents an age-old dream come true. Round-the-clock, ultra-precise position fixes from space to units of the fleet everywhere, in any kind of weather, anywhere in the world.